Alrighty. Well, thank you all for waiting. Really appreciate that. But in the meantime, hopefully you appreciated just like the chats, little small conversations if you have participated. And yeah, let's get started. So, hello, thank you all for attending the last of a many wonderful ML lecture series from our Global Teaching Fellows. This is awesome. This is the last one. And if you haven't participated or seen the last few of ML lectures from our Global Teaching Fellows for this year, you can feel free to check them out at the video listing of our channel right here. Feel free to check that out. And then also we'll announce that on Twitter and some other forms of social media as well. So feel free to subscribe to those mediums. And yeah, just like watch out for the links as well. I am Raul, and I am a teaching fellow volunteer as a part of Delta Analytics. But first of all, what is Delta Analytics? Delta Analytics is a community of 90 plus data scientists, economists, analysts, and software engineers seeking to leverage their data skills for the welfare of the community. While our primary background is in the private sector, we apply our skill set to facilitate progress in the nonprofit world. We find the data questions of social sector fascinating and address them in eye towards high impact and sustainability, where our mission is data is powerful and anyone should be able to use that for the changing their community or communities. We partner with nonprofits again and communities all over the world to build technical capacity that generates positive social impact. And today, coming back to the topic of our discussion, we will have Aseda Addai-Deseh speaking about k-means clustering. Just a little bit about the speaker before I bring her up. Aseda is a first-year graduate student of computer science at Stevens Institute of Technology, New Jersey, North America, particularly USA. She was previously a data scientist at Wave 2 Analytics Limited in Ghana, where she worked on customer, retail, and marketing analytics. Aseda serves as the lead and co-lead of various data science and machine learning communities in Ghana, the Pi Ladies Ghana Data Science Community, Indaba X Ghana, and the Women in Machine Learning and Data Science Accra chapter. A little bit more. Aseda holds a bachelor degree in computer science from the Kwame Nkrumah University of Science and Technology in Ghana. She believes that women and children have a huge role to play in social science, technology, engineering, and mathematics, and is a STEM advocate. Now, everyone, may I bring up to the stage Aseda?
Hi, everyone. So today we are going to talk about the k-means clustering algorithm. And don't worry if you have no idea what this is or about computer science. I promise it's going to be beginner friendly. You're going to love and enjoy it. You're actually going to relate to it. So let me know in the chats if you can see and hear me clearly. Right. So we've heard a lot about me, so I'm going to skip this. And the agenda for today, before we look at the k-means clustering algorithm, I'll first give you a background to it. So k-means clustering is first an unsupervised learning method and also a clustering technique, right? So we are going to take a look at what unsupervised learning is, what clustering is, the types of clustering we have, and then we'll go into the k-means clustering itself. We'll try to understand the intuition behind it. We would validate our clusters, go through a Python demo to show how it's done in Python, and then we would close with a few strengths and challenges of the k-means clustering algorithm. So what is unsupervised learning? So I would define unsupervised learning as a field of study where unstructured or unlabeled data are analyzed to make sense of it. So you may be wondering what machine learning is, right? So machine learning is basically a kind of AI that learns from experience, learns from past experience, and then tries to predict some future outcome based on the understanding of that experience. So in our case, since we are dealing with machine learning and data science, the experience here will be the data that is fed into the model, right? So since we have unsupervised learning, I'm sure you're also wondering there must be supervised learning somewhere. Yes, and you're right. So there is supervised learning, but the focus of this talk is on unsupervised learning. So that's what we are going to spend some time on. And unsupervised learning, we could do various tasks such as finding interesting patterns within data, condensing data to form meaningful representations, and also finding groups of similar entities within a given data set. What is clustering? So clustering is basically the task of grouping data points based on similar features such that each entity or all entities within a group are very alike to one another in that group and very different from entities in another group. So say for example, think of your friends, your group of friends that you have. Let's say I ask you to cluster or to group your friends into, for example, gender. You may decide to put all the boys in one group and all the girls in another group. If I ask you to cluster based on maybe where you know them from, you may decide to have all your high school classmates or all your high school friends in one group, all your university friends in another group, and all your primary school friends in another group, right? So that's typically clustering. If I give you a basket of fruits, of different kinds of fruits, and I ask you to cluster them or put them into groups, say based on the sizes. You may put the watermelons and the pumpkins in one group. You may put the oranges, the apples in another group, right? And if I ask you to cluster them based on colors too, you may have a whole different set of groups from the basket of fruits that I give you. Now, finally, when I give you, or if I should give you news articles based on different topics, right, and I ask you to cluster them or put them into groups of similar articles, you may decide to put all the articles on politics on one side, all the articles on sports on another side, all the articles on, let's say, tech in another group. So you can see that clustering is something very normal that we can all do as humans. And for the K-means clustering, it's just a way to teach the computer how to do this for us. So there are different types of clustering. There are a lot of them, but here I state hierarchical clustering and K-means clustering. If you'd like to know more about clustering, on the last slide, I have a link to some articles on that. But for our talk today, we are looking at the K-means clustering algorithm, so we will dive right into it. So K-means clustering is an algorithm. And for those of you who get scared when you hear the word algorithm, an algorithm is just a funky word, a funky computer science word that we give to a series of steps to accomplish a task, right? So K-means clustering is basically a series of steps that is used to partition a given data set into K clusters. So that's where the name comes from, K clusters, such that each data point is assigned to a cluster with the nearest centroid or center point. So this K here could be any number, but our job is to find what is the optimal number for K, right? So don't worry if this definition is kind of hanging loosely around your head. That is the purpose of this talk, and I'm going to expand more on that. So first, let's look at the intuition behind K-means clustering, right? So for a moment, I want you all to imagine that we own a restaurant and would like to set up 3 new branches based on, we want to set up 3 new branches in our city based on the locations of our customers, such that each branch is easily accessible to each customer, right? So let's say this is our data we have it represented on a number line, and the gray points represents the distances of our customers in kilometers, say from the city gates, right, from a particular point. So looking at it again, okay, with the human eye, if I should ask you to come up with 3 groups or 3 particular areas or positions where we should place our restaurants based on the data we have or the information we have on the locations of our customers, just by looking at it, we will see 3 distinct natural groups coming out, right? So this is what we did, or this is what we can see as humans. And let's see how the k-means clashing algorithm is going to perform this same task, but by using its special algorithm. So in the algorithm, first we need to determine our k. And as I said earlier, k is any number at all, but we always want to find the optimal number. So we determine k, and in our problem here, we want to set up 3 restaurants. So our k would be 3. Great. Moving on, the next step is to initialize k points randomly as cluster centers. I have this number line here, and now I have 3 different points, which are going to be my cluster centers, or the centers of the restaurants. Let me see the hypothetical positions of our restaurants, right? So right now, they are in random positions. Okay, so the next step is to assign each data point to the nearest centroid. So remember, centroid is basically the center of a cluster, or the center position of a cluster. So we have to assign each data point to the nearest centroid, right? And to do that, we are going to take the distances between each of the data points and each of the cluster centroids and find the smallest distance, or the nearest distance, between any data point and any centroid. And we are going to assign each data point to the nearest centroid, right? So over here, just looking at it with our human eyes, we take the blue distance, the red distance, and the green distance, right? And we can clearly see that the blue centroid is closest to our very first data point. So the algorithm says that we should assign this data point to the centroid that is closest to it. So there we go. We have the very first customer assigned to a restaurant, to the blue restaurant. Next, we have our next customer, and taking the distances again, the blue distance, the red distance, the green distance, and we see that clearly this also is supposed to be assigned to the blue restaurant. The next point still assigned to the blue restaurant. Right. So here, this is where I ask you my very first question. So which color of restaurant should we assign our fourth customer to? I want to see that in the chat. Or if Raul, if you could come on and help me to see any answers that people are giving.
Yeah, can I repeat the question is which color of the restaurants for number 7?
Yes. Okay.
Looks like we got a couple of answers. We have from majority of a lot inputs coming in, right?
Okay, I see red. Leke says red. Amishadai says red. Okay, a lot of people are saying red. So excellent. You're all right. I can see that you're following. That's very good. So we move on to our next data point. So the second question comes here. Which color of restaurant should we assign our next data point to? Okay. Delta Shadow says green. Any other answers? Any other answers? Should we take green? Okay, since green is winning, so let's see what we have here. Great job. So it's green, right? The next data point, what do you guys think? Green for sure. Okay, green. Very good. You are all following, and I'm happy about that. So the next and the next and the next are all going to be green. They're all going to be assigned to the green data points because they are closest to the green centroid than to the red and the blue. Awesome. So we have our very first iteration of the k-means clustering algorithm. But are we done? We don't know. Let's go on to check if we are done. So the next says that we should compute new centroid positions for each cluster and make new centroids the cluster centers. So what we are going to do is, now that we have this, according to the algorithm, we want all the data points to be around or to be assigned to their nearest data points, right? To their nearest centroid. And want the centroid to be in the center position of the clusters. So right now, as we can see, the blue centroid is not in the center. We need to move it to the center position of this group. The red centroid needs to move to the center of this red group. The green point needs to move to the center of this green group, right? So boom, there we go. We have our new calculated centroid points. But are we done? Let's see if we are done. Okay, so as you can see, we have three groups, right? And even though we have three groups, we are looking for k of 3, we have three groups. I don't think we should be very happy or very satisfied with what we have now, because naturally, these groups don't look like natural groups. Okay, so let's see why. Step 6 says, if not converged, go to step 3. So step 3 says assign each data point to the nearest centroid. So convergence is basically the points where we get to and we realize that each data point is assigned to their nearest cluster, right, or the nearest centroid. And we can see that the blue points are fine, the red is fine, but the green, look at this very first green point, is supposed to be assigned to the nearest centroid. And right now, you can see that the nearest centroid seems to be the red centroid instead of the green. So let's fix that, right? Let's start taking the distances again. The blues, we can see that the blues are fine. This first blue point is fine. The other blue points will all be fine. This red point is perfect. It's in its perfect place because it's right on the centroid. The next point is this green. Okay, so taking the measurements again, we have the red distance, the green distance, the blue distance. So what should we assign? What color should we assign this next point to, this green point? Any answers in the chats? Any answers in the chats? The question is, taking the new distances, which color of restaurant should we assign this green point to? Should it remain green? Should it be assigned to blue? Or should it change to red? Okay. Someone says red. Delta Shadow says red. Excellent. That's it. That's it. It's supposed to be assigned to the red centroid because now it is closer to the red centroid than to the green. So moving on, we take the measurements for the next green point, the next, and the next. And we realize that all the green points seem to be okay because they are closest to their centroid than to the red or to the blue centroids. Great. The next step is to compute new centroid position for each cluster and make new centroids the cluster centers. So as you can see, we have three groups. We still have three groups, but our centroids don't seem to be in their right positions because they're supposed to be in the center of each group. So the next thing is to recalculate the centers of each of the clusters, and that is what we have here, right? So the blue points remain the same. The red moved to the center of the red cluster. The green also moved to the center of the red cluster. Great. So we have our three groups which look perfect. They look just like what we did when we just looked at it with our human eye and determined, okay, these should be the natural clusters. So we've seen how k-means clustering goes through a series of steps just to arrive at what we did naturally as humans, right? Moving on, we're going to look at validating k-means clusters. So in machine learning, when we build a model, we usually want to validate it to make sure that the model is performing as expected and is able to generalize on other problems in the real world and not just fit onto the data that we train it with. So in supervised learning, it's quite straightforward to do so because we have labels. But in unsupervised learning, we don't have labels, so we need to think of a smart way to do that. And I know of two methods. One is the elbow method, elbow, and we'll explain why it's called the elbow method soon. And the other one is the silhouette score. And in this talk, I'm going to focus on the elbow method. So let's see how the elbow method works to help us validate our k-means clusters. So basically, the elbow method is an experiment used to determine the optimal number of clusters within a data set. Remember that in k-means, we always want to get the optimal k number, right? To be able to get that naturally occurring groups or clusters within our data set. And how it does it is that it plots the average within cluster sum of squares as a function of the number of clusters. And the elbow point of the curve is picked as the ideal number. So moving on to explain that, this is how the elbow method looks, right? It's basically like an experiment, and we plot for, we do the k-means clustering for different cluster sizes. So here we have from 1 to 9, right? And we determine something called the average within cluster sum of squares, which basically means the measure of compactness of each of the data points, right? So if we have one cluster, say we want to put all our data points into one group, you realize that the data points are going to be sparse. They're going to be widely spaced out, right? And so that's how come here for one cluster we have a very high value for our within cluster sum of squares. Then when we move on to two clusters, now we are kind of breaking the data set into two. Okay, so we're going to have certain points very close to one another and other points also very close to one another. And so the average within cluster sum of squares or the average compactness within each of the groups is going to drastically reduce among each of the clusters. So that's why we have that drastic reduction. So if we further break down the data set into more clusters, so we have 3, 4, 5, and 6, and so on, this compactness is going to increase, right? And so there's this particular point at which, after a very drastic or after a series of drastic reductions in the compactness, the next increment in the cluster size just reduces the compactness by very little amounts, right? So at that exact point where at a very drastic reduction, we do not have so much of a reduction in the compactness, that's our ideal number of clusters we should use. And that's the elbow point. So can you see that it looks like an elbow and then the point over there, right? Moving on, we have a check for understanding. So I would be going to the charts now. I have a few questions for you. I want to check if you've been following. And let me see who gets the correct answer the fastest. So my first question is, clustering is a supervised learning. So clustering is a supervised learning technique. Were there any answers while I was away?
I believe the answer was false for number one.
Great job. That's it. So you've all been following, and I'm very happy about that. So it's correct. It's actually false. And the next question is, in K means clustering. K is the number of clusters we end up with. True or false? Let's see who gets it first. Leke. Leke got that first. Great job. The last question is, the elbow method is the only way we can validate the number of clusters determined by k-means. Okay, people are typing in the answers without me reading out the questions, but that's great. I see Sarah, I see Delta Shadow and Jao, and yeah, that's correct. Excellent. So moving on to our Python coding demo, just to show how k-means is done in Python code, I will switch on to my Google Colab notebook, and let me know if you can all see clearly. Great. So we have seen the intuition behind k-means, and now we are going to look at how it's done in Python, right? So first of all, I'm going to import some libraries. I have the matplotlib library here to help us with graphing, to see our data points and all that. I have the make blobs from the scikit-learn data set library. We have the k-means from the scikit-learn cluster library as well to help us do all this. So let me run this code. Great. So next we're going to use the make blobs to generate some random data sets, right? Or some random data points for our data set. And here we are specifying that our samples should be 150 and the number of features to be 2. Previously, we looked at just one feature, the distances in kilometers of our customers, right? And that was just one feature. But here we are looking at 2 features. So you can take it as, say, the X and Y coordinates of our customers, right? Their exact location. Then we are specifying 3 centers so that we can have 3 groups. And we are specifying that our cluster standard deviation should be 0.5. That's like a measure of the compactness. And then we are specifying a random state of 0. So the random state is just so that if you take my notebook, you'll be able to reproduce exactly what I'm about to do. Moving on, we have our libraries imported. We've created a sample data set. We go on to the visualization, and in the visualization, we just plot our data points, right? And this is what we have. We have scattered data points forming 3 different groups. Great. Then we go on to create an instance of our k-means algorithm, right? And over here, we are going to specify the number of clusters. Remember the k clusters, the number of clusters we want to have here, which is 3. Then we specify an init of random. Remember when we're doing it intuitively, I mentioned that we were like the very first initialization was going to be random, right? So this is where we specify that initialization of our centroid, our center points. And as usual, the random state is just to make my work reproducible so that when you take my code, you can get exactly the same results. Right. So we are going to go on to predicting the classes, right? And we call the fit predict method here to give us the labels we should assign to each of our 150 data points. So we have 0, 1, 2, 0, 1, and 2. Okay. And in computer science, we usually start counting from 0. That's why we have 0, 1, and 2. And these are just labels specifying that this data point is supposed to be in cluster 1, cluster 0, or cluster 2. Right. So now let's go on to visualize. I have a piece of code here to visualize our clusters that the K-means algorithm was able to come up with. Okay, so there we have it. From here, from this graph, our K-means was able to determine that there are 3 naturally occurring groups in this data set, right? Which we have customized to have green squares, yellow circles, and blue triangles, right? And the stars, the red stars are just showing the centroids or the center points around which each of the data points have been clustered. Great. Let's move on to the elbow method for validating our K-means algorithm. So here it's basically a loop that we have here, which is going to do the experiment of calculating the K-means for when we have different cluster numbers, right? So from cluster 1 to cluster 10. And we are going to plot the inertia, which represents the compactness, the measure of compactness that we get from each of the iterations. So you realize that here if we have just one cluster, we have a very large inertia, which means that the points are very spaced out, right? When we go on to have 2 clusters, the inertia reduces drastically because now we have 2 different groups and each of the points are now very close to one another than before. Then moving on to 3 also reduces, 4, 5, 6 also reduces, but in very, very small quantities, right? So remember the elbow point, right? It is the exact point where after a very drastic reduction in the inertia, there is just little reduction in the inertia following an increase in the number of clusters, right? So 3 here, our elbow point shows that this data set has 3 naturally occurring clusters. Great. So let's do a few changes here in order to make this fun. Let's see what happens if we should have 4 clusters instead of 3. So I'm going to run this and run that, predict, and run this. You realize that now we have 0, 1, 2, and 3. Okay. So now we have an extra group or an extra label for an extra cluster. Then, okay, so before we visualize this, I need to uncomment the part of my code that will make us see the 4th cluster, right? So in Python, we use the single quotes 3 times. It's one way to comment out code so that that part is not run. So let me run this quickly and boom, we have our 4 clusters. But you can see that the algorithm has divided the bottom group here into 2, right? And it doesn't look pretty at all. It looks like something has been forced down here. And when we look at the graph for the elbow method, you realize that this is the inertia we have for 4, and it's just slightly different from the 3. Okay, just slightly different from the 3. And the result we have here doesn't look natural. It doesn't look pretty. Right. So let's go on to look at what will happen if we should have 5 clusters instead. Let's see what the model would do. Okay, so now we have from 0 to 4 clusters, and I would uncomment part of my code so we can see all the clusters. and we have 5 groups now. So you can see that the model also divided this top cluster into 2. So now we have this divided into 2, this divided into 2, and then this group here, right? You can see that this also doesn't look pretty at all. It doesn't look natural. It looks like something has been forced down there, right? So now let's look at what will happen if we have if we have 2. This time, let's go below our optimal and see what happens. So I'm going to run this and run that. And now we have 0 and 1, right? And let me comment out the parts of the code we do not need now. Okay, and run this. Okay, so now see what the model is thinking. It's seeing that, okay, the 2 groups at the top look very similar to one another. So let's put them in one group and then put our centroid in the middle here. And then I put the second centroid in the middle down here, right? And look at the inertia we had there, right? So we can see that the elbow point gives us a very good indication of where the ideal or the optimal cluster numbers or cluster number should be. So let's move this. Let's change everything back to normal, back to what is reasonable. So we change this back to 3 and run it. Run again, going back to normal. And get this comment out. Run that. And we are back to normal again. So this rounds up the coding part. I'll quickly switch to my presentation, my slides. And in conclusion, we can see that if we want to set up our 3 new branches, right, in such a way that each branch is easily accessible to each customer. So remember that we are assuming that the data set we use is the location of our customers, right? Say the X and Y coordinates of them in our city. And we have just run through a k-means clustering algorithm, and it tells us that, okay, these are the optimal points to put our restaurants, right, in such a way that each of our customers will be able to access the restaurants easily, right? So as you can see, the points here, there, and over there would be the ideal centroids for or the ideal positions for our new restaurants we want to set up, right? So to round up everything, we are going to examine some advantages and challenges of the k-means clustering algorithm. For advantages, first, it's relatively simple to implement. You realize that from what I just did, right? And it's easy scale to large data sets, adapts to new examples quickly. And for the challenges, so you realize that because we are actually dealing with distances, okay, cluster centers could be negatively influenced by outliers. If you have outliers, it's going to really mess up your clusters because of the measurements that are being used in the calculations. The next challenge is that it's unable to scale properly on data with a large number of dimensions. Initially, we looked at just one dimension, which is just one feature. Then we looked at another example with 2 dimensions. Okay, so in machine learning, or in k-means clustering machine learning, when you have so many dimensions or so many features to cluster, it's a bit of a challenge for the algorithm. So usually we employ the use of dimensionality reduction techniques to be able to aid the algorithm do a better job. Finally, clusters are dependent on initial centroid values. So remember that I said that we randomly initialized as centroid points, right? As centroids. So imagine if we had a very large data set, wherever we start the initialization from is actually in a way going to affect the number of clusters we come up with. So these are a few advantages and challenges of the k-means clustering algorithm. So to go further, I have included some links on so many things on clustering, k-means, on other clustering algorithms, and supervised learning, and so on. So when you have the slides, you could have access to that as well. So on this note, I would like to round up my graduation lecture on k-means clustering. And if you have any questions, I would like to take them now. Thank you.
Great. Anyone, any questions to what Aseda mentioned? Feel free to enter them in the chat right now. And Aseda, I have a question for you.
Okay.
Why do they call it the elbow method? Why not like the hockey stick method or like, I don't
Why is
know,
it?
the eye method or
You said
just,
why is it
yeah.
what?
Why is it called the elbow method? Like jokingly.
Okay, the elbow. You're
Elbow
asking why it's
method,
called the elbow method.
yeah.
Okay, so because it looks like an elbow, right?
Huh.
Doesn't it
Yeah.
look like an elbow to you? So like a
Yeah.
bent arm and then the elbow, right?
Yeah.
Okay, so are there any questions for me?
Hmm. If there's not, I can ask one more question. Are there any other
Okay.
alternatives to the k-means clustering?
Yes.
Okay.
So apart from k-means clustering, okay, you mean like unsupervised tasks, unsupervised methods. So apart from k-means clustering, there's also a method called association rules, which is used to find um, associations within data sets. So, for example, let's say you have a shop, a retail shop, and you want to find what kind of items are usually bought with other items, right? You can employ the use of association rules. And then also, dimensionality reduction in itself is also a kind of unsupervised learning as well. Yeah.
Mm. Mm. Okay. Looks like we have another question in the chat. We got one from, sorry if I pronounced this incorrectly, Joa, but it was like the same question there. Another question is, what would you like people to know about your Delta Analytics experience?
My Delta Analytics experience. So it was truly amazing. It's it has been really amazing, eye-opening. I've learned a lot about teaching, delivering technical content, preparing a lesson plan, thinking of what exactly to say at what minutes, and it's really helped me improve upon my teaching skills, especially when it comes to technical content like this.
Mm-hmm.
And um, yeah, I think that anyone at all who wants to learn how to teach better, wants to learn how to teach machine learning better, should definitely take on the Global Teaching Fellowship Program. It's been really eye opening.
Mm-hmm. That's a good answer. I like that. I really like that.
So, if there are no more questions for me, I would like to thank a few people. I'd like to share my screen and thank a few people.
Mm-hmm.
Okay, so first of all, I'd like to thank Abigail. Abigail is the lead for Pi Ladies Ghana, and she's actually the one who pushed me, let me say, who encouraged me to take on this program, and I'm really grateful to her for that. Next, I want to thank Rao, you, for being such an amazing buddy and mentor. I want to thank Melissa, Sarah, and everybody on the team, Brian, Ali, Amanda, Alicia, for all your time, all that you put in, all that you've invested into me, and all the times that you looked at my slides, gave me feedback on my talk. I'm really grateful. I'd also like to thank my other fellow and my other teaching fellows. Yes, I also like to thank them for the diverse experiences they brought on board. I learned a lot from all our meetings, and I'm very glad I took on this. So, are there any more questions for me? Um, did you?
Looks like it's pretty good so far. Hmm, nothing yet, but in the meantime,
Is there any other
we give like
question?
a round of applause.
Okay, if you have more questions, you can email me or DM me on Twitter, or we can connect on LinkedIn. Right.
All right. Yeah. So to what Aseda just said right now, if there are no additional questions, reach out to her on those particular mediums as well. I think I don't know if she said that she's also on Twitter as well, so feel free to reach out on Twitter as well, or she'll provide information there. We'll have this content available soon after the recording. It will be available on the Delta Analytics YouTube channel, and then we'll also be sending that out on like Twitter, LinkedIn, Facebook as well. If you want to share that with other individuals, or just peers and just in general. But yeah, Aseda, we really thank you for your time and the opportunity to help us learn more about k-means clustering. And now I feel like we're all just clustered and learning a lot more about k-means clustering. So really thank you for that.
My pleasure.
Yeah. So with that being said, we're going to end this broadcast, and yes, from me to Delta Analytics, and then to Aseda, have a great day, and then also have a great weekend, and good next week as well.
Bye.
All right, bye everyone.